Okay, so hi everybody. So it will be like I guess reading kind of seminar, more than you know. It's not a research talk because I haven't done any research on this topic, but so I'll tell you about this famous algorithm that is like what was discovered 15 years ago for testing primality in polynomial time, deterministic algorithm, and then I'll tell you some background along the way, and I'll try to present the whole thing today. It's actually it's very clever, but it's not very complicated. So I'll start with some introduction, some simple properties that one needs to know about primes. What do we actually want? Tell you something about primes being NNP. Tell you about some randomized algorithms that existed, and then I'll go to the Agrawal, Kayal, and Saxena algorithm. Okay, so well, the first, okay, if we want to test if a number is prime efficiently, well, we have to come up with some properties that prime number possess, and to come up with an algorithm, we have to come up with some properties. Well, the first idea that could come to mind when you think of how to test whether a number is prime or not, just try trial division, just take numbers from 1 to root n, and then one by one test whether your number is divisible by that or not, and if it's not, then it's prime. Another idea that you may have in mind is to use this very old result about prime numbers due to Wilson, which tells you that number is prime if and only if it is -1 modulo n. So this n-1 factorial is -1 modulo n if and only if n is prime. And well, to see this, means I'll do a couple of warm-up simple statements like that, so that we get used to some notation and also some of the things that we'll need later. The proof is very easy. Well, of course, if n is composite, then n divides n-1 factorial, and it's I mean, that would be already good enough. So n is comparable to 0 mod n. So I use this vertical line to denote the fact that the left number divides the right number. So if n is composite, then this is what happens, and if not, then well, clearly n is not comparable to 0 mod n, and that would be already a good enough test, checking whether it's 0 non-zero mod n. But just let's see why it should be exactly -1. Well, what can we say? That if n is prime, so if n is prime, then for every number a from 1 to n-1, there is a unique inverse. A -1 such that a -1 times a is comparable to 1 mod n. And just we simply split all the numbers into themselves and their inverses. And in most cases, almost in all cases, a and a to the minus 1 are different, if a to the minus 1 and a are the same, then it means that basically a squared is comparable to 1. And the only solutions that you get for that are a comparable to plus minus 1 mod n. So basically, the inverse of plus 1 is plus 1, of course, and then the inverse of minus 1 is minus 1. So every other number together with, when you do this product n minus 1 factorial, together with its inverse gives you 1. And then the only thing that is left is minus 1, for which inverse is itself. So this is why you get the minus 1 mod n. And also 1, but 1 doesn't influence it. So we just split n minus 1 in pairs and n minus 1 factorial in pairs, and then have only minus 1 left. Okay, so this is the Wilson's result. Another thing one can think of is the following lemma.
So Andrey, you want
yeah.
to say that these are terribly inefficient?
Yeah, I'll say it in a second. So all of that is inefficient. I'll just give another simple lemma, and after that I'll say that all of that is inefficient.
In your proof, I'm confused about your proof. Isn't n always 0 mod n? I don't get what you're writing.
Oh, sorry. This was n minus 1 factorial, of course. Yeah. Sorry. I took the wrong n minus 1 factorial. You see, too much stress with Corona. Yeah. This is what I meant. N minus 1 factorial is either 0 or non-zero. Is the proof clear? Any questions about that? Okay. Yeah, good. It's good that I make mistakes. At least I hear the audience. Otherwise, it's kind of eerie. Okay. So another simple lemma that one can try to use as a criterion for being a prime is the following. So n is prime if and only if x plus 1 to the n is the same as x to the n plus 1 modulo n, as not as numbers, but as polynomials with integer coefficients. So we are saying that if you open up this x plus 1 to the n, then the coefficient in front of each term, except for x to the n and 1, would be 0 mod n. And basically it accounts to saying that n choose k is 0 mod n for every k equals 1, etc., n minus 1. Yeah, okay. So if n is prime, then obviously this is true, just simply because well, no other number that we would get opening up this binomial coefficient, I mean every other number except for n would be smaller, and then they're smaller, thus they are relatively prime to to n. And we'll have a multiple of n. So when we open up the binomial coefficient as n factorial divided by n minus k factorial times k factorial, the only factor that would be divisible by the only factor that is divisible by n, which is prime, would be n itself, and thus it would be 0 mod n. But if n is composite, then we can take, say, some prime factor p, and then we can look at and choose p, and this thing would be n times n minus 1, etc., n minus p plus 1 divided by p factorial. And well, none of these numbers is divisible by p, right? Because p is a prime. Well, and thus even their product is not divisible by p. And whatever degree of p we have in the prime factorization of n, n divided by p will have that degree by 1 less. I mean, if p just appeared in the first power in the factorization of n, then n divided by p would not be divisible by p, and in any case, this thing is just not divisible. It's not divisible by the right power of p, and thus is not divisible by n. So we managed to find a particular coefficient, binomial coefficient, that does not vanish in case if n is composite, based on any prime factor of n. Okay, so this is a bunch of possible criteria, and it looks like, well, all of that can be checked quite efficiently as a polynomial of n, but we actually want, when we ask for an efficient algorithm for primes, we don't want it to be polynomial in n. We want it to be polynomial in log n, that is a polynomial in the number of bits that you need to use in binary representation of n. And all these algorithms that we described before, including this trial division, require some polynomial number of n and not log n operations. Okay, this is our goal, to get a polynomial algorithm in log n numbers. But even before that, it's a valid question to ask. Okay, we don't know yet if primes is in P. Determining whether number of primes is in P. Is it in NP? Is it in co-NP? So this thing is actually not so difficult to show, and it's quite nice. So let's first see why. There is some sound. Can someone switch off this noise? Oh, cool. Thanks. Okay, so let's first check that primes are in co-NP. That is, we have an efficient certificate that would show us that a number is not prime. So whenever a number is not prime, we have an efficient certificate for that. And in this case, it's very simple. So we need to check efficiently. We need to have an efficient certificate for a number being composite. So our witness certificate would be just 2 integers smaller than n that multiply to n. So very easy. And this shows that primes are in point P. If we want to show that primes are in NP, it requires quite a bit more work, or quite a bit. No, it requires also like 5-10 minutes proof, which I'll give. But it's much less obvious how to come up with such a certificate, unlike in the CoNP case. So we'll use some well, algebraic properties, I guess, of primes. Notably we'll use this lemma, which tells us that if n is odd, I guess testing even primes is easy. So we can assume that n is odd, and n is the prime power if and only if the group, the multiplicative group Zn of Zn star, so the group of all numbers that are relatively prime to all residues that are relatively prime to n. This group is cyclic, so n is a prime power if and only if this group is cyclic, which means that there exists an element G, generator G, such that the whole group is generated by its powers. So we take G, G squared, etc. And you get all the elements from a Z and a star. And well, the number of elements, I guess, would be n minus 1 only in case if n is prime, but it would be smaller in case when n is a prime power. But anyway, so this set generates the group. And as a witness, this would be the key thing. So now I'll describe you a witness which someone should provide us, and after that we can efficiently check whether the number is prime or not. So witness, it's generator G of Zn star. It's good. So we have a generator, and we would need to figure out that is actually a generator. For that, we need to check that basically G in smaller power, G gives 1 only in large powers, essentially, and modulo n. And for that, we'll need the factorization. So to check this property, kind of, we need a factorization of n minus 1. P1 to alpha 1, etc. P m to alpha m. And okay, assume that we believe that this is indeed a prime factorization. It's some factorization, and it's easy to check that it's some factorization, but to make sure that each of PI's is prime, we need to apply the same certificate recursively, but this we can put aside for the moment. Let's believe that this is actually a factorization of n. of n. And what we need to test is so once we have this, we test if g to the power n-1 divided by pi is 1 or not 1 mod n. So basically, if we believe that p1 to the alpha 1, etc., pm to the alpha m is the prime factorization of n, then
Sorry, Andrey, n or
yeah.
n-1?
n-1, sorry, again, yeah, prime factorization of n-1, yeah, of course. Thanks. So if we believe that p1 to the alpha 1, etc., pm to the alpha m is a prime factorization of n-1, then we just need to check that G actually generates the Zn star, and then to check this, you need to
sorry, don't you need also to check that G to n-1 is 1?
Well, I mean, yeah, well,
because
I mean, we can.
n-1 is not necessarily the order of multiplication.
Yeah, sure, but okay, this is a technicality. We can immediately check in the very beginning. I guess we check if n is a power of a number, and this is in any case quick. And then if it's a power, we stop. And then from now on, we assume that n is not a power, and thus
but Andrey, you do need to check that G to the n-1 is 1 mod n. Anyway.
Why? n-1 is not.
Yeah. Okay. I mean, we. Okay. We do need to check that G to n-1 is 1 mod n. Yes. Okay, but my point is that you can discard prime powers in the very beginning just by discarding powers of numbers, and yeah, we want to check that this is a generator. So to check that this is a generator, we verify that G to the n-1 is 1 mod n,
And then you don't need to check the powers.
Then
yeah, but that's true, but you don't. I mean, I think it's good to assume that the number is not a power, and this is no loss of functionality because this is easy.
Yeah.
I don't understand. I thought the group size was n-1, so G to the n-1 is always going to be 1 mod n.
No, the group size is not n-1. The group size is the Eulerian function of n.
I see.
And yeah, so you are not guaranteed that the group size even divides n-1. If in case it's prime, then it's n-1, and in case it's not prime, I guess like it's prime power, it would be what, p times, if it's p squared, it would be p times p minus 1 probably. Okay. So once again, okay, we have this generator that was given to us. We have a prime factorization of n-1, and now we check that G to the n-1 is 1, and G to the n-1 divided by pi is not 1. So what then? It means that, well, we know that, and we'll see it on the next in a minute, that an order of an element, so the minimum, the degree in which, the minimum degree in which it gives 1, modulo n must divide, well, the order of an element divides an order of a group. And if g to the n minus 1 divided by pi is not 1 modulo n, it means that the order of the element g must be exactly n minus 1. Because if it's not n minus 1, it must divide n minus 1. And this proves us that G is indeed a generator, and thus we can conclude that n is prime. Well, the nuance here is checking that this is indeed a factorization, and checking that this is indeed a factorization requires a certificate of the same form for each pi. So here we also need certificate or witness of the same form for each pi. But it doesn't blow up because, well, since numbers p1, etc., pm multiply to n minus 1, then, well, you can think of, like, if n has k bits, then the total number of bits that you need to represent p1, etc., pm would be also roughly k. And in like, log k steps will converge, or in k steps will also converge to like very small prime numbers. Okay, so is this clear? This primes in NP?
Yes, if you want a feedback.
Okay, good. Great. So now I'll give you a couple of kind of results from elementary number theory and group theory. I don't know that we'll need, which kind of I don't know. Maybe I should have given them just before the testing that primes are in NP. But anyway, so these are the things that we essentially used above. So one thing is Fermat's little theorem. So if n is prime, then a to the n is comparable to a modulo n for any integer a. So in particular, if well, if a is non-zero, then a to the n minus 1 is comparable to 1 modulo n. And from here, like motivated by this kind of result, we can define an order of an element. I was also vaguely referring to it above. Of so I guess this order of m modulo n. We define it only for m's that are relatively prime with n. And it would be the smallest possible integer a, such that, well, positive integer a, such that m to the a is 1 modulo n. So in the previous, on the previous slide, when we were looking at the generator, the order of the generator was order n of g was n minus 1 on the previous slide. Okay, and then we have Lagrange's theorem, which I also mentioned, that if you have a group, a finite group G, and you have its subgroup, then the size of its subgroup must divide the size of the group. And in particular, this implies that, well, order n of m must divide the size of z n star because if you take element M, then its powers is a group, I mean, relatively prime to N, then its powers form a group, and the order of the element is simply the size of the group. And this is what we were using on the previous slide. So that, you know, if an element to the power n minus 1 is 1 modulo n, but to the power n minus 1 divided by any prime factor of n minus 1 is not 1, thus its order must be exactly n minus 1, because it's clear, because it divides it, but does not divide any proper factor of n minus 1. Okay, great. So this Fermat's little theorem actually, if we look at it, this brings us to possibility of another possibility of an algorithm for testing prime. So what if we just try and test this property for some integers a, and then look what happens. So and in particular, it brings us to a randomized polynomial algorithm based on that. So we may ask a question: is there an a such that a to the n minus 1 is not comparable to 1 modulo n, provided that provided that n is composite. So if n, okay, if n is composite, then is there an a such that a to the n minus 1 is not comparable to 1 modulo n? And if yes, then how do we find such a thing? I'll cheat here a little bit, and I'll tell you where I'm cheating. But what I'm telling you is not very far away from the truth. So the first kind of observation in this direction is due to first theorem in this direction is due to Miller. So there will be a bunch of the results from the 70s, who tells us that basically it's enough to check one of the first a1 to 2 log squared n, assuming generalized Riemann hypothesis. And one will find such an a, essentially. And then, so this kind of gives us actually a polynomial algorithm to check whether a number is prime, polynomial in the number of bits, because we have to check a certain property for log squared instances of a, and actually doing this exponentiation can be done in log n time by getting, well, first a, then a squared, taking it modulo n, then a to the 4th, taking it modulo n, etc. So by repeated squaring, this can be done in log time.
We needed that for the NP algorithm too, right?
Sorry?
We needed repeated squaring for the NP algorithm to run in polytime, right?
Yeah, right. I did mention it at that point, yes. But yeah, this repeated squaring can be checked efficiently. Well, the only drawback is that we need generalized Riemann hypothesis, and it's something hard and not clear if true. Something like one of the major open problems in mathematics, and not clear if true. So that's not so good. But then Rabin suggested a simpler test, just take A at random, because if there is such A, apparently there is at least a half of A that at least a half of A are such that they will violate this property. So why is that? Because actually this thing, all the numbers that satisfy that their n-1th power is actually 1 mod n, this thing is a subgroup of Zn star. So the order of H by Lagrange theorem that we saw must divide the size of Zn star, which is just the Eulerian function. That I wouldn't introduce new notation. And clearly, if you have a number, so if you have a number not in H, then these things cannot be equal. And if two numbers are not equal and one divides the other, then it must be at least twice smaller. So the order of H is at least twice smaller, thus at least a half of A violate this property.
What about Carmichael number?
Yeah, well, it's exactly the place where I was cheating. So actually, this is not the test for primality in the sense. It's a test whether a number is prime or Carmichael. The problem is that this thing, so this thing is violated. Well, I guess not violated by Carmichael, but anyway. So there are Carmichael numbers which are composites, and for which you cannot find such an A that is comparable, not comparable to 1 mod n. So Carmichael numbers, with respect to Fermat's little theorem, behave as prime numbers. So problem Carmichael numbers. Composites for which whatever number you take, it would satisfy A, and A to the n-1 is 1 modulo n, provided that A is relatively prime to n. But essentially, the algorithm of Miller and Rabin exploit not Fermat's little theorem, but some very closely related property. So roots, basically based on roots of possible roots of x squared equals 1, and also do check similar things. So essentially, this is what happens, just for a slightly different property. So Miller and Rabin gave this in the 70s, and this was, as far as I understand, the beginning of randomized algorithms. So somehow Rabin's observation, then another algorithm by Soloway and Strassen, also from the 70s, were first great success of this randomized algorithm. So if you want to, to check explicitly if P is a prime or not, or N is a prime or not, then you can do this conditioned on some very hard results in number theory. But on the other hand, you can just do it in a very efficient and simple way by taking numbers at random, and you don't need to condition on anything. So this was a big success, and that became then that became the start of the randomized algorithms. And what people tried to do later on is they tried to first get a, randomized algorithm, and then to de-randomize it. So that was the kind of general approach for many problems. And getting closer to our main topic today, Agrawal and Biswas I think probably a year before they actually, or a year or two before that they, Agrawal and his students published the paper, they came up with another randomized algorithm. Where instead of testing Fermat's little theorem, they would test this Child's binomial theorem, which we saw above, but now they'll try to do it also in a, I mean, in an efficient way, because we saw that we cannot check all the coefficients. So what is the possible efficient way of doing so? The Child's binomial theorem just gives you this, if n is prime, so this part, just mod n. But to simplify this for computations, you can also take all of that modulo a certain low degree polynomial f of x. So say f of x has degree order of, well, some order of polynomial in log n, then once you take all the coefficients modulo n and modulo that polynomial, suddenly the thing that was polynomial in n becomes polynomial in log n, and possible to check efficiently. And Agrawal and Biswas basically came up with an algorithm that allowed for algorithm for checking if number is a prime, a randomized algorithm, in which what they did is they checked this identity for two polynomials modulo a random polynomial f of x. I'm not going to get into more details, but at least the way I guess Avi puts it is that it's a very it's a valid question to ask, how come number theorists thought about this polynomial algorithm for primes for a long time, and at the end it was a bunch of people that were not number theorists but rather computer scientists that came up with an algorithm for that. And then the reason, the suggested reason, is that actually they came to it from a very algorithmic perspective. So first they came up with a randomized algorithm for testing if number is a prime, and there was a bunch of different randomized algorithms, and then they tried to de-randomize it. And in this case, there is a nice way to de-randomize it without conditioning on any hard result. Unlike in the case of Euler's, or not Euler's, Fermat's theorem, if we want to de-randomize it, we need some very heavy tools. And in this case, it turned out to be that you can just de-randomize it without any conditional without using any conditional results. Okay, so maybe any questions up to this point? Because now I'm going to finally go to the algorithm of Agrawal and Kayal and Saxena. Okay, so let's look at the algorithm. Actually, it is a very interesting story in itself. So I said that these people were not number theorists, but even more than that, Kayal and Saxena were, I think, bachelor students at the university in Kanpur, I think, probably where Agrawal himself is teaching. But anyway, at an Indian university, and that was their semester project, as well as it was, I think, for Biswas, I think. So there were these two papers, both semester projects of Agrawal with his bachelor students, and ended up being a major breakthrough. So that's probably one of the most successful semester project that never happened. Okay, so let me describe the algorithm. It's written down here. The first step, which we generally, as I mentioned already, ignore, is we check that check whether n is a perfect power of a number. Then the second step, we find a certain number r such that the order of n modulo r is large. So n to small powers doesn't give 1 modulo r. We check that n is relatively prime with all numbers smaller than r. So these two steps are kind of technical and easy. And the main check that we do is we check this polynomial identity, this child's binomial theorem, modulo n, so and modulo x to the r minus 1, where r is this number that we found in step 2. So you can kind of think of it as a mix between Fermat's little theorem test and this Agrawal-Biswas test, where you check the child's binomial theorem modulo a random polynomial. So now we replace that random polynomial that we saw by some concrete polynomial, x to the r minus 1, very nice concrete polynomial. And we check this identity for a's that range in a certain interval from 1 to square root r log n.
So Andrey, you want to say that such an r will be small itself, like log n to the 4th or something?
Yeah, okay. So I wanted to say it a little bit later, but yeah, so we can find, today I'll show you how to find r at most log n to the 5th. So once we do the check in step 4, the main check, so checking this child's binomial theorem for a particular polynomial and for an interval of values of a, we output that the number is prime if all the steps have passed positively. So that n is not a perfect power, that it's relatively prime to some small numbers, and that this polynomial identity in step 4 holds for all values of n. So this is the algorithm. We'll see it in on the next slides, but in small. So I guess before the break, what I'll do is I'll just go through the kind of time analysis and why, like what should we expect from the steps, and then we'll take a short break. Okay, so this is the algorithm. Well, I left some space for myself to write down some notes, but okay. So the first, but I'm not sure that I'll write much. So the first step is checking that n is not a, or maybe wait, before I go into time analysis, let's again look at the algorithm and then convince ourselves that prime numbers will pass this. Clearly, prime numbers pass the first step. The second step is guaranteed to us for any number. Third step, again, the prime number would pass because they're relatively prime to anything. And fourth step, prime numbers will pass again by the, essentially by the lemma that we proved above, except we proved it with x plus 1 to the n. And here it's x plus a to the n, but the proof is exactly the same. The binomial coefficients will vanish in case when n is prime. Intermediate binomial coefficients will vanish. Even modulo n, you don't even have to take modulo an additional polynomial. So clearly, if a number is prime, then we output yes. We output prime. Okay, and what about the time constraints? Okay, the first step is roughly log cubed n operations, checking that n is not a perfect power. Well, I've already mentioned that it's easy. Maybe I just don't want to spend time on it. I mean, there are lots of ways to do it. So checking for every possible power that n is not a to the k for all k from 1 to log n. For each power, you need log squared n steps. Second step, as I already mentioned, in a second step, we can find R to be at most log to the fifth. And moreover, we can find R prime. So this is slightly inefficient in the optimal algorithm. If we go for the optimal running time, then you don't want necessarily R to be prime, but in our case, since we just want a polynomial algorithm, and having a prime R would simplify slightly the presentation, we'll find a prime R. And this is essentially, this thing is a corollary of the distribution of primes theorem. That we have roughly n over log n primes in the among the first n numbers. Third step is well, Euclidean GCD the GCD algorithm of Euclid, and again checking for each number requires roughly log n squared steps, and when we do it for all of the t from 2 to r minus 1. By the way, if you cannot see, I hope that you can see this part, because it's somehow important in case you haven't, digested this. If you can't, tell me, I'll zoom in. And the fourth step, well, maybe that's the that requires the most work. That's the most time-consuming step. Well, again, for each value of a, what we do is we repeatedly, for each I equals 1, etc., log n, we calculate x plus a to the power 2 to the I, and it would always be a polynomial of degree at most 2r. And then once we calculated it, we take it modulo n and xr minus 1.
Yeah, I think we have to take modulo n all the time, because otherwise the numbers will go too big.
Yeah, at every step. So basically, we calculated this polynomial to for I minus 1, and then we just take a product of those two, and then we simplify the numbers, and we simplify coefficients and simplify to a polynomial of degree at most r-1, just by, well, it's actually in case x modulo x r minus 1, it's very simple. We just take powers that are greater than r, and just, you know, power x to the r plus a, we just replace by x to the a, because in our in the space that we live in, when we take things modulo xr to the minus 1, xr is 1, so x to the r plus a is x to the a. So it's a very simple reduction. So anyway, so from the previous step, we get a polynomial of degree at most r with all coefficients is r minus 1, or with all coefficients in Zn. We multiply 2 copies of that, and again simplify it to the same kind of polynomial. And well, each of the steps is again easy, requires r times log n. I guess for each I you need r times log n operations. So yeah, I guess this is a good point to stop at the moment. So we have maybe I'll go back to the algorithm so that you can look at it again. So we've figured out that the algorithm, provided that in step 2 we indeed can find r that is small, will work in if we resume the time constraints that I put there. It was r to the 3/2 log cubed. That was the dominating one, and this is roughly log to the, I think, 10 and 1/2 of n. Algorithm runs in this time. Well, while with the fourth step being the most time-consuming one, and primes are indeed passing the test. The main and only question that is left is why composites fail this test. So this exponent, speaking of the exponent, the best we can hope for somehow is 6. And I think that this was eventually reached by some, I don't remember who, but basically improving step 2. I mean, since r should be at least log squared n, we cannot hope for anything better than 6, because r to the 3/2 would be then log cubed, and in total it would be a log to the 6. And I think 6 plus lit law of 1 at least was reached via more complicated analysis of the same algorithm. Okay, so let's take a break. You think so? I think I'm doing exactly.
Yeah, okay, let's see. Anyway, you should start.
Okay. Okay. So where were we? So this again is the algorithm, and the essential steps are step 2 and 4, and what we are left to do is to figure out why composites fail this test. So on a very, I guess we can, let's go there. Okay, why the composite non-perfect powers cannot pass 4. There's a very, on a very broad kind of vague and very imprecise and I don't know, maybe premature way of saying it is we'll define a certain group of polynomials such that on the one hand, I mean, assuming that a certain composite passes the test, we'll define a certain group of polynomials such that on the one hand, this group must be small because n is composite. And on the other hand, this group must be large because this polynomials pass test 4. This number passes test 4. Somehow, this is a very, very vague idea. And to get there, we'll first have to go through a bunch of definitions. So it's like next 15 minutes would be sort of technical. So yeah, bear with me. Okay, so first we have n that is not 1 modulo r, because we agreed that n has large order, and in particular its order is not 1, so it's not comparable to 1 modulo r. N is composite, but relatively prime to all numbers at most r. Well, this in itself implies that there is a prime factor of n such that p is bigger than r and p is not comparable to 1 mod r. So this p would be somehow essential in building in making the group of polynomials small. Well, and I mean, I guess in some sense both ways it would help us to show us the group of the polynomials that I told you about would be large, but it's much more important for showing that this is small. Anyway, okay, so we have this p, and the other property that we agreed that n must satisfy is that for every a from 1 to l, which would stand for the square root r log n, x plus a to the n is comparable to xn plus a modulo n and x to the r minus 1. So this is just step 4 of the algorithm. I just rewrote it here. So this is what we agree on. So now we get this p, a prime factor of n, and by its primality we can say that x plus a to the p is compared to x to the p plus a modulo p. Again, this is just Child's binomial theorem. But from here, so from this thing and from this thing, we can actually derive the following thing, that x plus a to the k is comparable to xk plus a modulo p for every k in a set I, which is n over p to the I, certain property for n and for p, that x plus, well, basically x plus a to the n is xn plus a, and the same for p. Then we get the same property for n over p, and as a matter of fact, for all numbers from the set I, where I is n over p to the I, p to the j, for I and j being positive integers. So I remark here that, okay, so we need modulo p and x to the r minus 1. Yeah, this is what we want. I remark here that since this property holds modulo n, it also holds modulo p and x to the r minus 1 because p is a divisor of n. So this is fairly easy to check, and I'm not going to check it. I don't know if you have any questions about this part. Okay, so now because we have this p, now we have a whole set of numbers I for which the polynomial behaves in this nice way, and we can even push it a bit more. We can define a set of polynomials which look like products of x plus a to some non-negative powers, where a is ranging from 1 to L. Remember that L is exactly this 1 to L is exactly the range for which we assume that property 4 holds. So again, a simple check is that for every k from I and for every polynomial f from for every polynomial f from this set of polynomials, we have this nice property that f of x to the k is f of x to the k modulo p and x to the r minus 1, and all of that is really just chasing the definition. So it's very it's a very easy check. Okay, so this actually brings us to the definition of two main objects for the proof. The certain group of numbers, which is just I modulo R, and a certain group of polynomials that I'll talk about in a second. So what about I modulo R? What do we know? So it's a multiplicative group. Because I mean, we can look at the definition. The definition is in the corner actually here. So these are these numbers, and obviously, if you take two numbers of this form and then you take a product, then it'll give you a number of the same form. Okay, so and then here we use that. I mean, of course, all these numbers are relatively prime to R. So it's a multiplicative subgroup of ZR star. Okay. Then the other important, the important thing that we know about this group is that its size is actually quite big. We denote it by T, and it's at least log squared n. So this is by the choice of R. So why is that? Well, because n has large order modulo R. We agreed that n has this, at least that order, at least log squared order, and n to the power I belongs to this group, and thus just elements n squared, etc., n to the log squared n give us different elements. Okay, so the group is relatively large, and the next thing that we want is a group of polynomials, and that would be the most kind of technical thing. We take our set of polynomials that we defined, this products of x plus a, where a ranges from 1 to L, to non-negative integer powers, and then we take it modulo some h of x, which I haven't defined, but what's important is that h of x would be irreducible. So h of x h of x is irreducible, and this will give us that well, actually just irreducible factor. Let's put it immediately. Factor of x r minus 1, such that well, reducible factor of xr minus 1 of degree, let's say of degree bigger than 1. X to the r minus 1 obviously has an irreducible factor x minus 1, but we want an irreducible factor of bigger degree. So first observation that we have is that the set F, which is defined as the ring of all polynomials over Zp factored by this h of x, is a field.
Sorry, so h is irreducible over integers or modulo something?
It will be irreducible in Zp.
Okay.
Irreducible in Zp, irreducible factor of in Zp. So this thing is a field, and what we want is that, actually, I mean, maybe I need to erase a little, or let me do a manipulation here. Just dezoom this thing to have more space. Again, so what we actually want from this H is that the degree of X in this field would be R and nothing less. So we want that so apart from it being irreducible and thus working with a field, we also want that x to the r, well, is 1 in F, and x to the I is not 1 in F for I equals 1, etc., r minus 1. And well, why am I talking about what do I mean by that? So how can one think about this this field F? Is just we start from a field of field Zp, So residues modulo P. And then we look at this polynomial x to the r minus 1. This polynomial in field ZP has only one root, x equals 1. That's the only root we have. Because R is relatively prime to P. And
R should be relatively prime to P minus 1.
R should be.
It doesn't matter much because you told we can choose R to be prime.
Yeah, R is prime in any case. Yes, exactly. So that
and P minus 1 is not divisible, so
yeah,
that's okay. But
yeah, R is relatively prime to P minus 1, and so we adjoin. I mean, x is another root of this polynomial that we adjoin to a field ZP, and we get this field F, which is just basically the the span of so you can look at F as Fp of x factored by h of x, and you can look at it as kind of the if you forget about multiplicity, you can look at it as a vector space over Zp, where bases would be formed by the degrees of x. So x is the, anyway, I'm sounding a bit confusing, but anyway, so we're adjoining another root of this polynomial to the field, and we get a bigger field since since R is a prime, the degree of any element that we added must, in a similar way to Lagrange's theorem, must divide R. But since R is a prime, the degree of any element would be either 1 or R. Degree of an element is this. So and the degree of if the degree of element is 1, it means that it belongs to the initial field, and if it doesn't belong to initial field, then its degree is not 1, and thus the degree would be R. So essentially, what we need here is what we need here is this property, and in case when R is prime, it's kind of straightforward when you enlarge your field, because whatever you add will not be will not have degree 1, and thus it must have degree R.
Andrey, this field is simply the finite field with P to the R elements, right?
Yeah, so this is a finite field with P to the R elements, of course, yes. And yeah, and yeah, the well, you can say this argument in I don't know, in a little bit more complicated way for any R, but I just stress that anything that we need here is that h of x is of degree bigger than 1, so that we actually enlarge the field. and that we have this property that I pointed out here. And this property is straightforward in case when R is prime.
Well, it should be of order P to R minus 1, I think, because otherwise X cannot have order K. Order R. I'm sorry.
It should be.
So this is the final field of order P to R minus 1.
P to the.
Because its multiplicative group should have an order divisible by R.
I guess it's the degree of H, really. It's P to the degree of H.
Yeah, the order of it would be P to the degree of H, of course.
Yes.
But obviously, but and H of X is so H of X must be a factor of X to the R minus 1 divided by X minus 1, because, well, we have to exclude X minus 1, obviously. So I'm not sure if actually automatically X to the R minus 1 divided by X minus 1 is irreducible, but anyway, we take any factor of that.
No, it's not.
In general, it should not be, but yeah. So, I mean, I don't know if R is prime, if it changes anything, but maybe if R is prime, this is my point, that maybe if R is prime, it is actually irreducible.
But it doesn't matter. You take
but it doesn't matter.
Irreducible polynomial.
But so you take any factor of that, whatever order this have, the only thing that it will have order P to the degree of H. Again, the only two things that I need from this field, from this polynomial H, is that first F is a field, and this is why we need irreducibility. And the second thing is that X seen as an element of this field, because this field is, I mean, you can identify kind of elements of the field with polynomials that that we had in FP of X before factoring. What I want is that if you look at X as an element of this field, then X to the R obviously would be 1, but I don't want X to the I to be 1 for any smaller I. And this is automatic because R is prime. Okay, so these two properties, field and sorry, but it's field and the other property underlined. Okay, so once we have these two properties, we are ready to go for the proof. So the main idea of the proof is the contradiction between these two things, that this polynomial group is large and the polynomial group is small. So it would be large because of property 4 or proposition I mean this proposition that these polynomials behave interestingly with respect to X, and we'll show the following bound, that it's at least t plus L divided by t minus 1. On the other hand, we'll show that G poly is small and is at most actually n to the square root of t, because n is composite. Okay, so these are the two things. If you compare those two quantities, we know that t is at least log squared. So this thing would be definitely at least 2 to the log squared n, because both t and l are at least log squared. And this thing would be at most, or maybe I should write something like, yeah, 2 to the log squared n. Very roughly speaking. So if t is roughly log squared, L is even bigger, then that thing would be at least 2 to the first thing would be at least 2 to the log squared, and the second thing would be 2 to the log squared. So this would be a contradiction. This is contradiction.
Yeah, make one of the inequalities strict.
Make okay. Let's make one of the inequalities strict. For example, that one.
But what was t?
T was the order of the group genome.
So it could be much greater than log squared.
It may be greater than log squared, but I mean, I'm doing then it would increase this thing even more. The thing is that this, I mean, this as t grows, this grows faster than the other one, because there we take square root of t. I'm writing very roughly. That's. So maybe one way to put it is that this thing yeah, I mean, I want to leave it as I said. So it should be clear that as t grows, the first this binomial coefficient grows much faster than n to the square root t. And if t is roughly log squared, then you see the difference between these two. Or I don't know. I can of course do these calculations, but I don't think it's essential. It's
no, it's not.
It's kind of straightforward, I think. Okay. Okay. So now we have to show these two things, A and B. So let's start with G poly being large. Why is it large? So a reminder, L is roughly square root, L is square root R log n. These are the tests for which, these are the values of A for which we tested, and T is the order of the group genome. Okay, so how do we prove it? This quantity that you see here is actually a number of certain polynomials, and this is how the proof would go. So actually, interestingly, both this lower bound and upper bound, the proofs are very similar in spirit. You just you deal with you basically say that a polynomial of degree d can have at most d, well, have exactly d roots. You cannot, if it has a certain polynomial has d plus 1 zeros, then it's 0. This is the proof for both upper and lower bound. So t plus L, choose t minus 1. is just the number of polynomials of degree at most t minus 1 in pole. Because, well, we had this monomials x plus 1, well, x plus 1, etc., x plus l, and then we rose them in different powers. So this is just the just counting how can you get degree t minus 1 or at most t minus 1 by taking products of these polynomials. So the first thing to observe is that all these polynomials are different in f p of x. This is because L is smaller than P, basically. So this is the only thing to check. L is smaller than P, thus all of them are different, and actually we get roughly that many polynomials of degree at most t minus 1 in pole, even once we take modulo P. So given that there are that many polynomials, the thing to check is if we remind ourselves of the definition. So it was pole modulo h of x and actually modulo P. So we only need to check that once we take this modulo h of x, different polynomials do not become the same. So assume that, well, it happens. So if G belonging to pole are such that they have degree at most t minus 1 and f of x is equal to g of x in f. So now when I write this identity, it's again a polynomial identity, because well, we took two polynomials from pole. We can think of them as polynomials we may as well think of them as polynomials in some f of z, where z is the variable, just not to confuse it with x. So okay, so we are thinking about these two things as polynomials over our new field, and now imagine that f of x, the value of f of x is equal to value of g of x in f when we substitute, well, f, well, x now is an element of a field f, so we substitute it there. These two things are equal. Then same holds for any m belonging to I. And well, this is just the property that we had before, that you know, f of x to the m is equal f of x to the power m on exterior. Now we can use the identity that we have above, g of x to the m, and this is g of x to the m. So this is the proof for this thing. And well, all these values, x to the 1, etc., x to the m, are all well, contain all these values, they are different for m belonging to our group genome. Well, because the degree of we agreed that x is so here we use that x to the r is 1, but not for smaller r, and we know that m and r are relatively prime. Thus, all these x1, etc., xm are different when we run over elements. Well, whether m these degrees are running over elements of the group genome, and thus we get that f of like f of x. Okay, let me reduce the size a little bit. Yeah, I'm a bit sloppy with my writing. Okay, so we found. Let me restart it again because, and say it short because I think I was a bit confusing again. So we assume that the f of x and g of x for two low degree polynomials coincided in f. From there, we, using the properties of polynomials in our set pol, deduced that f of x to the m is equal to g of x to the m for any actually maybe this I should write differently. So different, just like that. X to the m are different for m belonging to group genome. So for any element of group genome, f of x to the m must be also equal to j of x to the m by the properties of our polynomials. But all these elements x to the m for m ranging over genome are different because of the way we chose our irreducible polynomial h of x. X to the r is 1 in f, and not x to the I is not 1 for anything smaller. And because m is relatively prime to r, all these things are different. Thus, we get that from here, we get that order of g num roots for polynomial f of z minus g of z. But we know that genome has size at least t, and the degree of polynomial f and g was at most t minus 1. So thus this polynomial must be is identically 0, is a 0 polynomial. So this proves that if we start from two distinct polynomials in Paul, I'll first say take them modulo p, get distinct polynomials, and then even when we look at which elements do they map in F, we will still get distinct elements. Because if f of x, the image of f, when we do this, f of x is equal to g of x in F, then as polynomials, f and g must be equal because we find a lot of roots. Okay. Is this clear, this part?
Yeah.
Okay, good. I mean, and so this was the kind of, I guess, more algebraic part. The second one would be a bit more combinatorial. So here it should be G poly is small. So how do we prove that G polynomial, G poly is small? So this is more, we'll use pigeonhole principle. And then again, similar polynomial technique. So we look at our set I, and now we restrict it. So this is essentially our set I, except we restrict the values of I and j to be from 0 to square root t. Since everything is taken, everything is taken mod R, and since the group order is T, and we have more than T different elements in this set, there should be two elements, M1, M2, that coincide modulo R. So that are the same, that correspond to the same element in the group, GNUM. So MI, MJ are the same in GNUM. Okay. Well, what do we get from here? We get from here that x to the m1 is equal to x to the m2 modulo x to the r minus 1. Just because M1, here it should be M1 and M2. Just because M1 and M2 are the same modulo R, we have this property, right? Because when we take modulo x to the r minus 1, it's just as we would look at the residues of the powers modulo r. This implies that for every f of x in the in Paul again, we have f of x to the m1 equals f of x to the m2 modulo p and x to the r minus 1. Just because, well, again, a very similar calculation, something like f of x to the m1 is equal f of x to the m1. Here we use that x, that mi's are coming from this group gnum, which is good with respect to this pole set. So we get this, and this is equal to f of x to the m2 just because they're equal. This is equal to f of x to the m2. Okay, so we get these polynomial properties, and thus now every f of x thought as an element of field f that belongs to the G poly is a root of y to the m1 minus y to the m2. Let's denote this polynomial by q. So q belongs to f of okay, before I wrote z, so let's write z, f of z. So again, a similar trick. We look at this polynomial q. We have one root from this equality, and then using our group G poly, we get lots of roots. And this implies that, well, the size of G poly cannot be bigger than the degree of Q. But this thing is at most n over p times p to the root t, which is n to the root t. Right? Just by the choice of where does m1 and m2 come from. So this is the part where we use the fact that n is composite and that that n over p and p are not the same kind of, so that n is not a prime power even. To basically, I mean, if n was a prime, then we could only hope to, we would have only I running, I don't know, from 0 to t, and wouldn't get any significant kind of any interesting bound on the degree of q. But here, since we have two kind of factors, then we can apply this pigeonhole to a set where I and j range from not from 0 to t, but from 0 to square root t, and yeah, well, get a good bound on the degree of this q, and thus get a good bound on the size of G poly. Okay, so this completes the proof. So we show that it's small on the one hand, on the other hand we show that it's large. Thus we arrive at a contradiction. Maybe let me very quickly, I mean, I'm running out of time, but let me very quickly tell you how to take R to be like, go back to the step R equals big O of log to the 5 and R prime. For this, we need the lemma, which is just equivalent to the primes distribution, or dense, I don't know, distribution, I guess, theorem.
Prime number theorem.
Okay, it's called primes number theorem. Okay. Prime numbers theorem. Okay. So the statement, this lemma, just yeah. Well, what does it tell us? In other words, is that the product of all primes from, say, log squared n to the log to the fifth n. This thing is roughly e to the 1 plus o of 1 log to the 5 of n, right? Just exponentiate whatever is written in the lemma. Then this is what you will get for n equals log to the 5. For instead of n here, this maybe is a bad letter. Let me write m, because we're using it for m equals log to the 5n and log squared n. And okay, so what we see is that the product of first, I mean, primes up to log to the 5 basically is large, but on the other hand, so recall that what we wanted is we want n to have large order modulo r, where r would be a prime. So on the other hand, if a prime number p violates 2, then it divides the following expression. Product for I from 1 to log squared n to the I minus 1. Because what does it mean that order of n is at most log squared n? It means that it must be some I, where I is from 1 to log squared n. And if an order of n is I, it means that n to the I is 1 modulo p. It means that p divides n to the y minus 1. So if we take a product of all these expressions, then p must divide, then whatever p that violates 2 must divide this expression, but this is at most n to the log to the 4th of n, which is 2 to the log to the 5th of n. And we see that this thing is bigger than this thing, thus there exists p that satisfies 2, that does not divide this expression, and that's satisfied. And then we take it as our. Okay. Yeah, so this is quite easy modulo the prime numbers theorem. Okay, I guess yeah, I guess that's it. I'm sorry for some messy parts. If you have any questions, then please ask.
So questions to Andrey. Thank you.
Thanks. Thanks for listening.
Okay, so what? Anybody wants to ask anything? No questions. Andrey, do you know if this was extended to an algorithm for testing primality in you know, in the integers of other number fields?
No, that I haven't seen anything. I mean, I haven't done very deep research on what was done afterwards, but at least from what I've seen, I didn't see anything like that. Yeah, but I know the tools look. I mean, it's simple, kind of simple algebra and combinatorics kind of combined. So that maybe I don't see a place where we would rely so much on number theory, kind of, except for maybe this lemma. This may be the place where actually you some non-trivial number theory, but all the rest is
it's not important
algebra
to
and
get there is a much weaker, much weaker analog of prime number theory that was probably known. I don't know, not
yeah, but it's,
you don't need, for this lemma you need a much weaker bound than the precise.
But if we look for other, for other primes,
there are similar. I mean, just from it follows from the definition of what a prime is that you can give such density. But I don't know. I'm just asking. Other questions? So I just want to mention that one reason I asked Andrey to give this talk is that there is an open problem which is either related to this or not, which seems very basic, is whether there is a polynomial time algorithm to generate a large prime. So I give you n and I ask you for a prime number bigger than n. Nobody has a polynomial time algorithm for this problem.
And the randomized algorithm is very easy, because you just, I mean, again, because of this lemma, you just sample a number at random from n2 to n, and then after I don't know, log n trials, it's positive probability that you'll get one prime number, and then you can test it.
All right, so let's thank Andrey.
Thank you.
Thank you.
Thank you.